Hello, and welcome to this film, which is all about looking at some examples of different molecular shapes. In this film, we're going to be referring to some terms which were mentioned in the first two films called VSEPR and molecular shapes. So if you haven't seen those two films yet, it might be an idea to watch them first, because otherwise some of these terms aren't going to make a lot of sense to you, perhaps. Okay, so the point of this film is to try and turn some molecular formulae into electron dot diagrams, which hopefully we're getting quite good at by now, and to use these electron dot diagrams to help us determine the shape of some what are called planar molecules. So molecules where all the atoms lie in one plane, or in other words, can be accurately drawn in 2 dimensions. Now we're going to start off by looking at carbon dioxide, so that's CO2, and obviously if you add up the valence electrons here, you're going to have 4 there, and 2 times 6 there, so a total of 16, or in other words 8 pairs. Now how do we arrange those 8 pairs? Well, we should be able to do that, but we'll end up with 2 double bonds around the carbon, which is the central atom, and 2 lone pairs on each of the oxygens. Now if we think about what's going to go on here when the molecule, I suppose, decides what shape it's going to be, then we need to consider the fact that there are 2 groups of electrons around this carbon, or in other words 2 charge centers. Okay, that's not to say that there are 2 bonding pairs. Remember, there are still 4 bonding pairs around this carbon, but they're not acting as independent pairs of electrons, because the 2 pairs that are in this bond are kind of stuck together. They're acting as one group, so one charge center, and the 2 that are in this double bond, the 2 pairs that is, are also acting as one group of electrons, or one charge center. So if there are 2 groups of electrons, then they're going to get as far away from one another as possible by being 180 degrees apart. Okay, and if they're 180 degrees apart, then that means these 3 atoms are all in a straight line, and that's why we call this shape linear. So anytime a molecule is in one straight line, all the atoms 180 degrees apart from one another, we're going to have a linear molecule. And that will happen anytime you've got 2 charge centers, because that's how they get as far apart from one another as possible. Okay, let's move on to something called a nonlinear geometry, or alternatively known as V-shaped and bent. Now in this molecule here, we've got SO2, right? So SO2 is made of 3 atoms from group 6. So we've got a total of 18 valence electrons, or 9 pairs. Okay, and if we've got 9 pairs of electrons, then using our usual rules, we'll decide that we've got 1 single bond between a sulfur and an oxygen, a lone pair on the sulfur, and also a double bond between the sulfur and the oxygen. Remember, these lone pairs around the oxygens, they're not going to determine the shape of our molecule. What we're going to look at in deciding the shape is how many pairs or groups of electrons, more accurately, how many groups of electrons there are around this sulfur atom. And we can see here, hopefully, that there are 3 groups, because these 2 pairs here act as 1. So we've got 3 charge centers, even though we've got 3 bonding pairs and 1 lone pair, right? Because 2 of these bonding pairs are inseparable. They're part of a double bond. Okay, 3 charge centers, you might remember, are basically going to, if this is our sphere, are going to try and be 120 degrees apart from one another. So in other words, they're kind of going to lie on the equator at 120 degrees apart. But remember, because this molecule only has 3 atoms in it, we're missing essentially one of these corners. So what we're left with is these 3 atoms here, and that's why this molecule is bent. So this lone pair of electrons is influencing the shape, but we don't take it into account when we're talking about the shape, because it doesn't form a corner, so to speak. Okay, let's move on to a trigonal planar geometry. We've actually got 2 examples on this slide of how this can happen, but only one is on the WACE course, because this molecule here is an octet molecule, or this ion here is this molecular ion is an octet molecule. That is to say, it's got 4 pairs of electrons around every atom. BF3 has only 3 pairs of electrons around the boron. So this molecule does exist, and it does exist in this form, but you'd never be asked to predict this because we're obeying the octet rule at WACE. Okay, so let's have a look at what we've got here. We've got the NO3 minus ion. So 5, 3 times 6, and then plus 1 for the negative charge. So a total of 18, 23, 24 electrons, or 12 pairs. Okay, and once we've decided that we've got 12 pairs, we'll see that we'll end up with 2 single bonds around the nitrogen, a double bond, and all these lone pairs on the oxygens, which, remember, we're not talking about a great deal in this film because they're not determining the shape of the molecule. What have we got around this central nitrogen atom? Well, we've got 3 groups of electrons, because remember, this double bond, in spite of the fact it has 2 bonding pairs, is acting as one group of electrons. So we've got 3 charge centers here, even though we've got a total of 4 bonding pairs, okay, because there are 2 bonding pairs in a double bond. What do 3 charge centers do? Well, they try and get as far apart from one another by being 120 degrees apart. And this time we have got that third corner, so this is going to be called a trigonal planar geometry because it's a triangular shape, but all the atoms are in one plane. Okay, well, hopefully that makes sense. If it doesn't, I hope you'll come and see me soon and ask any questions that you've got, or post a comment on YouTube. The next film is going to look at some other shapes in which the atoms are not all in one plane.